I mentioned to you that GPS units rely on relativity corrections. And this particular problem is one where you're going to calculate what is the error in the position of a GPS unit. And so we imagine that there is a GPS unit on the ground right here. And how bad would the position error be if we did not use a relativistic correction? Right? That's the gist of the problem. Right? We assume, and we will talk about this, we will assume that the true position is right between two satellites that are simultaneously emitting electromagnetic pulses. And the way a GPS receiver works is it uses it calculates coordinates by triangulation. So what it does is it says that if this satellite transmits its coordinates xa prime that was emitted at a time ta prime, and this satellite, which we call C, it emits a pulse at time x, or at a position xc prime and at a time tc prime, then the GPS unit here will receive those two signals. And based on the difference in time and the difference in position of the satellites, it will calculate where the GPS is. Okay? So in other words, in this simple example, let's suppose that satellite A and satellite C emit an electromagnetic pulse at exactly the same time in their coordinate system. So we're going to assume that that TA prime, so in the satellite's coordinate system, which we call TA prime, is equal to TC prime, which is either equal to 0, which we can assume is a reference time. You can call it 12:01 p.m. if you prefer, but it's a timestamp, and they were both emitted at exactly the same time in their reference frame. Now remember, the satellites are moving across the sky at a speed of about 4 kilometers per second, which is pretty fast. Do that miles per hour, it's well into the thousands. And they're moving in unison together. It is possible for all of the satellites to synchronize their clocks, and they do. So when they say they emitted a signal at the same time, here and here, they emitted the same signal at the same time. Now, at a later time, the signal is going to be received down here, and they're going to receive the timestamp and the position stamp, right? Now, if in fact they were emitted, for example, at the same time, and they travel the same distance, meaning they're halfway between these two, then the GPS should see that the time difference is 0. And if the time difference is 0 between the two, assuming they were emitted at the same time, then it must be halfway between A and C. That's how triangulation works. That it basically calculates the time, it looks at the time difference of the received signals, says, where were you and when did you emit those signals? Aha, you were here and you were here, and now I calculate what the difference in time is, and if this one was emitted sooner, then say this, I'm sorry, let me rephrase. If the GPS was actually located over here, and they're emitted simultaneously, then this signal will be received before this one, because it travels a longer distance from this one. So the GPS will say, oh, this is where I'm located. Right? If, on the other hand, the GPS is over here, and the GPS is over here, and these are emitted simultaneously, then this one will take less time to get here than this one. The GPS will say, oh, this one came first, and then this signal came second. I must be over here. And it's based on a time difference. Right? So using the time difference, it can calculate, and of course, knowing where they were emitted from, it can calculate where it's going to be found on the ground. Right? Okay, that's the basic idea of GPS. And up till now, we've assumed that these two were emitted simultaneously. And in the satellite's coordinate system, they were. They were, and the GPS receiver is going to see that timestamp when it gets the signal. They're going to say, oh, okay, what I see is that the signals, the TA prime equals TC prime is equal to 0. They were both emitted at time t equals 0. Right? So now let me calculate what the difference in my receive time. If the difference in the receive time was 0, for example, then, and they were equidistant apart in the sky, as I've drawn here, then it will assume, it will calculate that its position was halfway equidistant from these two satellites, time of mission. Okay. So that's a little bit about how it works. Now we get into the complicated part. The complicated part is that even though these signals were emitted simultaneously here, and that's what's transmitted, for the observer on the ground, one of these was emitted before the other one. It's the same problem as the rod inside the barn. Remember, with the rod inside the barn, Alice measured that the rod fit in the barn and both ends, and she did a simultaneous measurement on both ends and said the rod fits in the barn. But Bob was writing on the rod, and he goes, no. First, the right end of this end of the barn, like the rod hit that end, and sometime later, after this long rod goes through the other side, the other end of the rod gets in, and he says it's not simultaneous. Right? So we've got a similar situation here, and what we have is that there is, in fact, even though they emitted at the same time here, there is, in fact, from Earth's point of view, one of these was emitted before the other one. Okay? So here's what happens. If that's actually true, let's suppose that let's suppose that from Earth's view, so we'll say from the Earth view, satellite A emits pulse before satellite C. Okay? Then what's going to happen? If that's the case, the GPS unit is going to get this signal first, because in the real life, in the Earth's time, this one was emitted first, and then this one was emitted, so this one gets to the GPS before this signal gets to the GPS. Okay? But the timestamp said they were emitted at the same time. So the GPS thinks, oh, well, I must be closer to satellite A than I am to satellite C, because I received this pulse earlier. Right? And if I received it earlier and I believe this timestamp, I must be closer to A. I must be closer to A. So he calculates where he is. And the gist or the goal of this problem is to say, what is the error that the GPS calculates? And we call this error delta x. What is the error that position that GPS calculates if it ignores relativity? And by ignoring relativity, the GPS assumes that TA prime equals TC prime equals 0, because that's what was transmitted to him, and he believes that absolute time is absolute, and that all clocks are synchronized, and if they told me they were emitted at the same time, then by God, they were emitted at the same time. I get one signal before the other, it must be because I'm closer to one than the other. Right? But that's his mistake. His mistake is that he assumes that they were emitted at the same time in his frame as they were in the satellite's frame. Not true. Simultaneous in one frame is not simultaneous in the other. These two were emitted simultaneously in the satellite's frame that's moving across the sky at 4 kilometers per second, but they don't get emitted simultaneously when viewed from Earth. And the GPS needs to know that. If it doesn't, it's going to make an error. And your job is to find out what error would it make if it ignored that. And assume that whatever time is stamped on these satellites is exactly the same as that they believe that that was the time they were emitted on Earth. Okay, is everybody kind of clear on that? Okay. The magnitude of the error will shock you. And as I said earlier, you cannot do a turn-by-turn navigation if you don't make this correction. And then it turns out that gravitational effects are even larger than this, and that produce errors that are 3 or 4 times that have to be corrected. It turns out that clocks that are running in a strong gravitational field run much slower, significantly slower than clocks up in space or away from a gravitational field. Gravity slows down the rate of time, just as the traveling astronaut's time gets slowed down as observed from Earth. Okay? Anyway, that's general relativity. But the point is, the problem at hand is the one I described. Okay? So everybody good with that? It's a hard one to explain, but there's a long discussion in the handout. Okay. Okay, so with that, I think we will go on. So the next thing that we want to talk about today is relativistic addition of velocities. So how do we add velocities? Addition of velocities. We thought we knew how they add, and now we find out that, well, they don't really quite add that. So let's imagine that there are 2 reference frames, as we always do, and one of them is fixed to a train, and I'm going to draw the wheels of the train, something like this. And this train car is moving at some velocity, we'll call it v. And there is 2 observers, one riding on the train car and one that remains on the ground. And just as before, the observer on the ground is not at rest with respect to the train. So by the way, these axes are labeled x and y and x prime and y prime. They are real coordinates in space, just as we always would have thought of them being. And of course, this is Earth. This is Earth ground. That's the reference frame of the observer on Earth. And we're going to relate the following question. Suppose that we have an object on the train that is moving with some velocity, which I'm going to call ux prime. Right? So ux prime is the velocity of a particle. So I have some particle of mass m, and it's moving forward on the train. And so I can say that ux prime is equal to the change in the position coordinate with respect to the time coordinate, delta t prime. Right? So Bob is on the train, and Bob is measuring how rapidly the particle moves from point A to point B. He calculates the delta x. He finds out how much time it took, divides by delta t. He calculates a velocity in his reference frame, which is called ux prime. Okay? That's the velocity that he measures. All right? So now what we want to know is Alice, on the ground here, she's going to measure the velocity of the same object, which we'll call ux, and that is, in her coordinates, is delta x divided by delta t. So she's going to see the particle move, in this case, in the forward direction, and she's going to measure her own velocity. Right? Now, the traditional rule that we learned about adding velocities is if we were to do a problem in 253, for example, we would say that ux is equal to ux prime plus v. Right? I simply add the velocities. Right? So if I want to know how fast this particle is going for Alice, right, I simply find out how fast it's going for Bob, and I add the velocity v of the train. And that's how fast it's going for Alice. Everyone agree? I mean, yeah? We're good? Everyone understand this? Okay. It helps to see a few heads nodding once in a while. So, as I said, I'm not speaking Chinese or Mandarin or some other language. Okay. Okay. So stop me if something doesn't look right. That's important. Stop me if it doesn't look right. Okay. So we want to look at this, and now what it turns out, as we suspect, this was certainly not true when we were talking about light speed. If we were talking about an object of like light, this equation was clearly we found was not the case. But what is it for? In fact, if it was a light particle or it was a light beam, we would say that ux equals ux prime. That's what we would say for light. Right? But what happens if it's traveling slower than light? Right? So that's what we want to find out, because now we've got the spatial transformation between these two coordinate systems that we wrote last time, and I'll write them one more time again, and they are that you can say that x prime, which is the coordinate, right? So at any given point in time, this has a coordinate x prime t prime, and if you want to actually refer to a particular point and it helps you visualize it better, then if we call this point, this would be x sub a, for example, a prime, then at this point we know that it's at a coordinate x sub a prime at time t sub a prime. Right? That's the way we categorize that. So if I were to write it in that type of a format, what I would say is that xa prime is equal to xa, which is the coordinate in Alice's frame, minus v at the time t sub a in Alice's frame, divided by what we call the Lorentz factor. Or 1 over this denominator is what we call a gamma. So remember we said that we can also write this as gamma times x sub a minus v times t sub a. Okay. That's what x or x sub a prime is. Okay. Well, we know that, for example, we can relate that to velocity by saying that we started off. Remember, we started off that at x equals x prime equals 0, t equals t prime equals 0, right? So at time t equals 0, we assume that the origins pass by each other. They're just overlapping. They're just starting to take off. And then at any later time, this equation holds. But this equation always depends on this condition. And notice that the only time and place you can synchronize two clocks are at one point on the x-axis and x prime axis, and we take the conditions to be written in this way. Okay. So that's one way we can write. Okay, we can write this, and then another way we can write this is to say that. So this is the actually the delta x, right? Delta x prime, because we have xa prime minus 0, right? Because at time t equals t prime equals 0, the particle was at the origin. So if I go backwards in time, then this particle starts at backwards in time, the particle starts at x equals x prime equals 0. At later time, it advances along the x-axis, and it has a new coordinate, and it's given by that. So I can say that this is equal to the velocity ux prime times t sub a prime, okay? Where this is actually delta t prime, which is equal to ta prime minus 0. Why? Because I started my initial measurement at x equals x prime when t equals t prime equals 0. Right? That was my initial starting point. So the delta is also equal to the coordinate at any later time. Okay, so that's the one fundamental equation that we have. What else do we have? We have the t prime, the time transformation. So the time transformation says that, another thing, right, is that ta prime is equal to gamma times ta minus v over c squared times x sub a. Okay. So this was the time transformation. It says if I know the coordinates that an event occurred or a particle existed at a certain point, this x, a, at time t sub a, I know where it's going to be, I know when it's going to be observed at the new coordinate xa prime by the transformation. So it transforms measurements in one frame to measurements in the other frame. That's why it is called the transformation. So now what I do is I combine these two equations. I substitute in this value of ta prime over here, and I can do a substitution. Everybody see that? I can put this in quantity in here for ta prime, and now what I do is then solve for x, for xa, solve for x sub a. So solve for x sub a, right? Everyone can see what I'm doing. I'm putting this expression for ta prime in over here, and now I'm going to solve for x sub a, and what I get is that x sub a prime, I'm sorry, we're solving for x sub a. X sub a is equal to ux prime, that's the velocity of the particle in the prime system, plus v times t sub a divided by 1 plus ux prime times v over c squared. Okay? That's what I get. Now, if I recognize that this is the distance that the particle moved in the n-prime system, and this is the time over which it moved that distance, then I know that in Alice's frame, she measures a velocity u sub x equal to xa divided by t sub a, which then is just equal to ux prime plus v divided by 1 plus ux prime times v over c squared. Okay? And that's my velocity transformation. It tells me that if Bob measures some velocity of 5 times 10 to the 6th meters per second, and the train is moving at 8 times 10 to the 7 meters per second, right? Then I know how to calculate u sub x as viewed from the ground. Right? And normally, as viewed from the ground, we said when velocities are going very, very slow, we expect this equation to be true. right? Because that's our normal experience. Velocities add. They add, right? Okay, now what we have is, there's the ux prime plus v in the numerator, but it's being modified by another term in the denominator, which only becomes significant when v or u, or both of these, become comparable to c. If each of these is less than, say, 1% of c, this term's going to be negligible. Not going to affect the velocity at all. We can throw it away. Then it's just ux prime plus v divided by 1. It's only when either v or ux prime become comparable to c that the correction kicks in. And it's just enough correction to make sure that no particle can go faster than the speed of light. Right? So now what we can do is we can plot this function. Okay? I can plot this function of the, what I will call the speed of the object on the train. So this is u sub x. And let me raise this up some. U sub x. So this is this, I'm sorry, ux prime. Do it correctly, ux prime. Speed of object from train. We'll say, or from Bob, right? Remember who Bob is. Bob is always the guy here that's moving with the train. And the train's, so the speed of object from measured from Bob, and I'll plot here u sub x, which is the speed seen by Alice, or seen by the Earth, and or Alice, right? She's on the ground, right? So I'm going to plot this, and what I get is, I get that initially, when the speed of the object on the train, from Bob's point of view, is 0, right here, then Alice is going to say it has speed v, which is, in this case, the velocity of the train, right? So v is always the relative velocity between the two. So that's the same v up there, it's the velocity of the train. So Alice, on the ground, just sees the object moving at the same speed as the train, because the particle's at rest in the train. Right? In other words, if this thing is stationary here, doesn't have any velocity for Bob, then Alice sees it just moving at the velocity of the train. Right? I mean, is this making sense here? Okay. Right? Okay, good, good. Okay, so that part is normal. And so if we were, well, let's curve it out. So what does this actually translate to? If I were to plot this out, what I would see is a curve that asymptotically goes up to a maximum value, which is c, and eventually, as it approaches the speed of light, as it should, in other words, it starts out going up, but then it levels out, and it stops at this point c. It cannot go faster than c. If I were to plot this function, which is the one we normally use at low velocities, then I would get another curve that goes linearly straight up. Initially it has the same slope as the relativistic curve, but it keeps going, right? This is what we call the Newtonian curve, or the Newtonian line, right? As the speed of the object increases, then the speed seen by Alice also increases because I add velocities, and this is the classical curve. But the relativistic curve is this one. Is this one, okay? The velocity is going to level out, and you can actually show that let's see if I can do it. I'll leave it at that. It levels out and it reaches a maximum. And just as light once it reaches the velocity c equal to 3 times 10 to the 8th meters per second, then it becomes the same for both of them. Now, it turns out that even though, as we said before, that y is equal to y prime, in other words, there's no contraction. There's no length contraction in y or z. No length contraction for the other two axes. Right? I'll just use y there because we're working in 2 dimensions, and I have x, y plotted there, but the same thing holds for z. So we can go, but however, as we've shown before, t is not equal to t prime. Right? So it turns out that if you do the derivation precisely, we can also get a transformation of the y velocity, the y velocities on the train relative to the Earth, as written as u sub y times the square root of 1 minus beta squared. I'm going to start using beta more because it's going to be easier than writing v over c over and over and over again. And this becomes 1 minus u sub x times v over c squared. Right? Now, notice that if velocity is very small compared to c, which it usually is, then this becomes u sub y. Well, x and y velocity are the same. I mean, the y velocity measured on the train is the same as the y velocity measured by Alice on Earth because there's no length contraction in the y direction. And at very slow velocities, that's exactly what we would expect. If you're not moving in the y direction, or the train's not moving in the y direction, then they should both see at low speeds, classically speaking, they should see at the same velocity. And they do when the speed is low. Because this beta goes to 0, this v over c squared goes to 0, so this becomes 1 in the denominator, and this just becomes u sub y. So at low speeds, it's the same as we expect classically. Okay. You can do your own playing with this. It's not hard to draw this curve out. If what you do is you can take v over c equal to 1/2, for example, and then let u sub x prime go from 0 to 0.99 times c, and put in values, and you can verify this curve. Okay, that's all I'm going to say about that. All right, that's part 1. Okay, now we come to first of all, any questions on this before I move on? You do have one homework problem that involves using a transformation of velocity equation, so you'll get some practice with that in your homework, not the one due on the 19th, but the one due on the 22nd, which should now be available, by the way. I think both of those homework assignments are now available for you to look at. Any questions for anyone? No questions. Okay. All right. I don't expect that means that you really don't have any questions. It probably means that you don't have any questions that you're prepared to ask at this time. Because one can ask a lot of questions even after you have a 5-week course of this. Okay, so the next step we're going to move on to is another principle of physics, which is called conservation of momentum. Conservation of momentum. And we expect that that the conservation of momentum, when I have two objects that collide together and they bounce off of each other, we have conservation of momentum and conservation of energy. So if I know the initial velocities and directions of the two particles before they collide, I can calculate the position, the angles and the speed of the particles after they collide. The conservation principle allows that. So we're going to do that, and furthermore, it's reasonable to expect that it doesn't matter how fast you're moving relative to these two objects or to your experiment to apply conservation momentum. We would expect that, for example, that if there were two balls that were collided together on the train and Bob calculates the final velocities based on conservation momentum, then Alice can also, she'll get different velocities, but she can use conservation momentum to calculate velocities in her frame. And she should be able to do that. The conservation law should be true in everybody's frame of reference. It's just like, you know, we discovered conservation momentum right here, but are we moving? Well, yes, we're spinning around the center of the Earth, you know, every 24 hours. The Earth is moving around the sun at 30,000 kilometers per hour. You know, there's a movement there. And the Earth and the sun is moving around the center of the galaxy once every 200 million years. 25,000 light years from the center of the galaxy. Everything is moving. Why would conservation of momentum only be good on this frame? No reason, right? Anyone moving relative to us should also be able to observe conservation of momentum. Right? There's nothing special about our frame that allowed us to discover this principle that only works here on Earth. Any other observer should also be able to apply conservation of momentum and calculate what happens to these two balls when they scatter. Right? Okay, so so that's the general idea. So the idea of this whole came about, or the whole reason for examining this, is that what Einstein found out was that if I assume that conservation of momentum holds in one frame of reference, and I apply these two velocity transformations in the collision process, he found out that conservation of momentum does not apply for anyone else moving relative to those two people, unless he modifies the equations of motion. And we'll talk about that in a second. So let's look at the experiment first. So the first part of the experiment is that we've got, let's talk about our frame S and S prime. So here's S prime. Now, there's two ways, of course, I can look at this. I can look at it from Bob's point of view, and from Bob's point of view, then Alice is moving in the opposite direction with velocity of minus v. So we're going to look at Bob's frame first. So let's look in Bob's reference frame. So we're going to take a very simple example where what we have is two equal massive balls that are going to approach each other, one from above and one from below the x-axis. And this has mass m sub a. And this ball comes in and it collides with another ball on the x-axis. And afterwards they scatter. So m sub a ends up over here, and the arrow of motion is like this, and then this ball coming down gets scattered in the opposite direction. Right? And we're going to choose a very simple type of problem where all the initial velocities are equal. So all initial velocities are equal. Are equal for MA and MB, right? Furthermore, we're going to assume that the mass of A is equal to the mass of B. Makes it even simpler. The balls have equal mass, and they scatter off of each other, and I apply conservation of momentum. I use conservation of momentum. And I show that the final velocity of particle A is equal to the final velocity of particle B. Right? And, or equal and opposite, I should say, because, well, certainly we can say that the y components are I'm sorry, right? This is right? The final velocities, yeah, the final velocities are we should say, yeah, let's say equal. So the conservation momentum applies, and we're able to calculate that this final velocity, Vf, for particle B, turns out to be the same, or I should say opposite. There should be a minus sign here, because I left out a minus sign. Should be opposite to the final velocity of particle B, right? And you do the experiment. Yes, it works. Conservation momentum is true. We all know that. We go home, it's fine, right? Now, the problem came in that when we apply and do the analysis in Alice's frame, then the problem comes in that we can show that momentum is not conserved. Momentum is not conserved if we apply ux prime and uy prime equations, the ones we just did, right? That those velocity transformations lead to a simple result, lead to the result that one can show, and we're not going to do it here, it's a really messy calculation, that momentum is not conserved. And we obviously know that doesn't make sense for reasons we just said. There's nothing special about momentum being conserved in this classroom and not for someone else in an airplane or a train going by, right? So Einstein did a very clever trick to make this work out. And what he did was he showed that he said, the way I can make this work, I can make momentum can be conserved in both frames. Is conserved in both frames. And the next part in both frames. If mass increases with velocity. Okay? In other words, in order for momentum to be conserved in this simple two-body collision of elastic collision of two particles, the only way that it could be made to work using these velocity transformations was to assume that the mass of A and B is equal to B only when the velocity of A is equal to the magnitude, I should say, when the velocity of A, the magnitude, let's do magnitude. So the magnitude of velocity A is equal to the magnitude of velocity B, right? And that's the only time which we can say these two particles have the same mass. At any other time, they have to be modified as follows. The mass, which we now define as the moving mass, the mass as a function of velocity, is equal to the rest mass, m0, when v is equal to 0. Right? That's when the mass is just sitting here on the table. I put it on a weigh station. I measure the kilograms. That object has a certain kilograms to it, and it's not moving, and that's the rest mass. Okay? So the rest mass in kilograms is the mass that it has when it's not moving. Right? And what Einstein showed was that the moving mass, which is what I have to use in order to bring back conservation of momentum, was equal to 1 square root of the same factor that we used for time dilation and for length contraction now also applies to mass. And is able to show that the mass, or the weight of an object, increases as it goes faster and faster. And, those of you that are physics majors need to go through this at some point before you graduate, but we're not going to do it here. But nevertheless, this is a rather revolutionary idea. Any questions on this so far? It was a necessary conclusion in order. I mean, there are really two principles of the special theory of relativity. One of them is that the speed of light is constant in everybody's reference frame, regardless of the motion of the source. The second principle is the laws of physics should be same in everybody's reference frame. Remember, we started off saying that Maxwell's equations should be the same, whether should be obeyed, whether I'm at rest with respect to two charges, point charges in the room, or I'm moving by them. Coulomb's law should still apply. Right? There's nothing special about the reference frame where these two particles are not moving. Okay? So we have the same principle going on here, that the mass is changing with velocity in order to make sure that conservation of momentum will work in every reference frame, regardless of how fast I'm moving relative to this experiment. I can't drive that for you, but I'm just stating that as a fact. But those are the two principles, right? Constancy of speed of light, laws of physics are the same in every reference frame. Okay? And we're applying that right now. We did it the first time to get the constancy of light. We're doing it the second time to state that it leads to, if conservation momentum is going to hold, this has to be true. All right, any questions on this? Okay, we're good so far. Great. Good. Okay, so now here's what we're going to deal with. So now, speaking of momentum, then we have a new equation for momentum. So before we get P equals mv, right? Now what we're going to do is say that P is equal to the moving mass, m0, divided by the square root of 1 minus v squared over c squared times v. Okay? Now what this means is, let's suppose that let's suppose that v is equal to 0.98 times c. And I calculate the Lorentz factor here, or the gamma factor, right? So we said gamma is equal to 1 divided by the square root of 1 minus v squared over c squared. And for this case, gamma is equal to 5. And if I do put in the velocity, supposing I just increase the velocity by 2%, not even 2%, 0.999 c. Right? Then now gamma is equal to 22. Okay? If gamma is equal to 22, that means that the momentum P was originally, which was equal to 5 times m naught times 0.98. Now P is equal to 22 times m naught times 0.98 times 0.999. Okay? So what happened was the velocity only went up 2%, but the momentum went up a factor of 4.5. Why? Because mass increased. Right? And that's an observable phenomena and effect that one can verify with subatomic particles. You know? We have subatomic particles that are moving around in a circle. Right? Supposing I have a ball on the end of a string, right? And I swing the ball. The more mass I have on that string to hold in its orbit, the more tension I have, right? To hold that in that orbit. Now, in an accelerator, I've got protons going around in a circle. And I make them go faster and faster, and I increase their velocity by 2%. The strength of the magnet that holds them in their orbit has to increase by 4.5 times. The strength of the magnet, because why? Because the mass of the particle going around has gone up by a factor of 4.5. The mass as viewed by me in the lab. If I slow down the particle back down to 0, then it's going to have just its rest mass, right? And so typically, if I have momentums that are or velocities, when we have velocities that are less than about 0.1 times the speed of light, then we can just write that p is equal to m naught times v. And this works perfectly well, right? But once we get up to values close to the speed of light, then we begin to modify that. Okay. All right, so it's just like another thing you have to get used to. Just like the length of an object gets shorter, the mass of the object gets higher. What happens to the mass density? Did you raise your hand?
No, I just wrote.
You just raised both hands, like what the heck? Well, what? Density is mass divided by volume. The mass is increasing because it's going faster. The length is getting shorter, which means the volume is getting smaller. So mass divided by velocity is getting higher, right? So the density goes up as a particle goes fast. Okay. We're all good with that, right? Okay.
So
Yes. Go ahead.
would that be true in your reference, or would that be true in the object's reference? So wouldn't that be, because you're viewing it, it's getting shorter, so
It's true in your reference.
Okay.
In the object's reference, remember the rest frame, nothing changes. It's like Bob riding on the rod going in the barn, right? I mean, he always sees a 20 kilogram bar and he always sees a 20 meter length rod, right? Then nothing changes because he's at rest. But when somebody looks at Bob's rod moving along, then they, looking at him, see it change. Okay? Good question. Yes?
So is that why they say it takes like an exponentially increasing amount of energy to get like a mass close to the speed of light? Because the mass is like increasing constantly?
Yeah. As you double the energy, you double the mass of the particle. But the velocity changes only, as I showed here. It only changes maybe at most 2%. Sometimes only 1%. But you have to add an exponential amount of energy to get a little bit more velocity, I guess is the best way to say it. Okay, we got one more important derivation to do before before we finish the concepts of relativity. Once we finish this, we finish the concepts, then on Tuesday I'm going to show you how to use these equations. And now that brings us to the point of kinematics. Okay. So, kinematics. Did I spell that right? Yeah.
yes.
Okay. So, what do we know about kinematics of a particle from Newtonian theory? Newtonian theory, we know that P, momentum, is equal to mass times velocity, and we know that kinetic energy is equal to 1/2 mv squared, which we can also write as P squared divided by 2m. Okay? Those are the Newtonian equations of kinematics. It relates, there are 4 variables: mass, momentum, energy, and velocity. Mass, momentum, energy, and velocity. And then they're all related. They're all related by these two equations, really. So we're going to have to replace those equations. And we can kind of see that already, because already we've replaced the momentum equation with this. So one of our new equations relating momentum to velocity is this equation, right? We've got one already. Okay, so how do we do that? Well, the way we do that is, and by the way, we are now going to derive one of the most famous equations in the history of mankind that energy is equal to mass times the speed of light squared. That's the goal of what we're after today, right? Finding out what that is. Okay. So here's what we have. The way we derived these equations in 253 was to say what happens if I have a particle of mass m and I apply a force F on it, then it will accelerate. So I apply a force F. This leads to acceleration. And acceleration leads to new velocity. And then we find out that we do work on the object, right? That if we apply a force F over a distance x, then the work done on the object is equal to the kinetic energy gained. Kinetic energy gained. So we're going to use that same principle here, right? That if I apply a force over a distance x, right, x, then I'm going to do some work on it. As a result, I've accelerated the object. It gets to a new velocity. I give it kinetic energy. The kinetic energy is equal to the amount of work I did pushing it. All right, everyone kind of remember that from 253? Does it ring a bell? Okay, so we're going to do the same sort of analysis here. And what we're going to do now is to say that we're going to use this principle right here and say that the kinetic energy, which I'll denote by E sub k, is equal to the integral of the force over the distance dx, over which I'm going to accelerate it. So say that I accelerated from x equals 0 to some maximum value x. And we are now going to replace the equation for force with the derivative of the momentum. So we're going to say that force is equal to the derivative of m times v. So by the way, I'm still going to use my old nomenclature u for the velocity of a particle, because remember, we don't want to confuse the velocity of the relative motion with the velocity of the particle. So u is the velocity of the particle, right? And I'm going to use that same nomenclature. So the derivative of momentum with respect to time, dot into dx. And I can write this as the, notice that I have a dx dt here. So by shifting the dt over to this side, I get that this is the mu times u. And now I'm going to integrate from u equals 0 to uf, right, or u final, some final velocity. And this goes from 0 to t, or 0 to some x final, and this is x final, and it's basically doing this interval. Okay, so now what I'm going to do is I'm going to apply the chain rule to the derivative. Now notice that now, as I accelerate and push this object, the mass is changing, right? Mass no longer comes outside. It depends on velocity, right? So what I'm going to do instead is to write that that the differential mu is equal to m times the differential of u plus u times the differential of m. I'm going to substitute that in, and I'm going to go that this is equal to the integral of m du plus u dm times u. Right? So I've just done the substitution of using the chain rule, basically using the chain rule for differentials. Okay. Now what I'm going to show you, and this is just a trick of mathematics, that this integrand right here is equal to, including the u, is equal to c squared times dm. So remember, dm is the changing of the mass as the object gets pushed, right? It's gaining kinetic energy. So as it gains kinetic energy, its mass is increasing. So delta m is the change in mass, right? That's what dm is. It's the change in mass, but I'm still doing the integral. Now, let me ignore this derivation here for a second and just take you through to what we get, because this is basically using some simple derivatives. But if I do that substitution, then what I get is, now I want to integrate this from the velocity or the mass of the particle m0 up to the moving mass, m, right? M of u. That's the moving mass. And m0 is remember, at x equals 0, u equals 0, so m is equal to m0, right? It's the rest mass. So I start at rest, I accelerate the particle. As I accelerate the particle, it gets a new mass because the mass is increasing, and I'm going to integrate this term from m0 to m. But c is a constant, right? So that comes out, and that's just equal to c squared times the integral of m0 to m dm, which is equal to c squared times m. And now we're going to reverse the order so you begin to see the famous Einstein equation, mc squared minus m0c squared. Okay? So, and what is m? M is the moving mass. So I can write this as m0 divided by the square root of 1 minus beta squared minus m times c squared minus m0 times c squared. But we said this 1 over the square root is gamma, right? So I can factor gamma m naught c squared out of both terms and write this as gamma minus 1 times m naught c squared. And this is the new expression for kinetic energy. Okay. So kinetic energy, now I can now express kinetic energy in terms of velocity, right? Because the velocity term is in gamma. The velocity term is 1 over the square root of 1 minus v squared over c squared. Okay. So kinetic energy depends on velocity, but not the same as before. Of course, as the particle begins to go slower and slower, I have to eventually show that this term times this term becomes 1/2 mv squared. When the particle starts going very, very slow, I should recover the Newtonian expressions for kinetic energy. Right? But if it's going very, very fast, then it's something different. Okay, so let's see here. So that relates, okay, so there's a couple profound things to state here. If I move this term to the other side of the equation, or I put it on the term with kinetic energy, then I can write that m naught c squared divided by the square root of 1 minus beta squared, right, is equal to the kinetic energy plus m naught c squared. Right? So we call this the rest mass energy of the particle. This is the rest mass energy. And the reason why this is profound is that the mass by itself inherently has energy contained in it. Even if the kinetic energy is 0, the total energy, we're now going to identify this expression as the total energy. And even if the kinetic energy is 0, by virtue of having mass, the particle has energy. mc squared. That's the energy. What that means is that if I were able to remove or annihilate or eliminate some of that mass, it could be transformed into other forms of energy. For example, if I want to make somebody wants to make a atomic bomb from uranium or plutonium, they are going to transform, they're going to take a certain block of uranium and they're going to make a reaction in which there is 1 less gram of uranium after the reaction. Where did that gram of mass go to? It went to kinetic energy of light, heat, neutrons, radiation. And if I have enough of those happening, that mass can be transformed into something else. That's the m naught c squared. The mass is no longer, has to be conserved. But the total energy is always conserved. Okay? So this is just another form of the kinetic energy. Okay, so this is the new expression that we have that relates the kinetic energy and the total energy. Okay? Okay, so one last thing is how do we relate momentum and kinetic energy? So let's see, how about momentum and kinetic energy, or what I call E sub k. How are they related? How are they related? Related how? Well, let's see. Here's what we can do to be able to get to that point. Let's write out our total energy equation again. So we're going to say that that the kinetic energy is that the kinetic energy plus the rest mass energy is equal to the total energy, E sub t. And this is now equal to m naught c squared divided by the square root of 1 minus v squared over c squared. And furthermore, we know that P is equal to m naught, oh, did I miss v? Remember I said I was going to keep using u's here for particles, right? So 1 minus u squared over c squared. So this becomes m naught times u divided by the square root 1 minus u squared over c squared. So this expression is a total energy. So now what I'm going to do is I'm going to square both sides. So the total energy squared is equal to, I'm going to square this equation right here, and I'm going to say this becomes m naught times c, m naught squared times c to the 4th. And in the denominator, I'm going to have 1 minus u squared over c squared, right? Because I squared the denominator, so I take out the square root sign. In the numerator, I have a 1, but I'm now going to add and subtract a quantity u squared over c squared. So I'm going to add it in, and then I'm going to subtract it out. And I'm going to keep going and reducing this. So then I get that this is equal to m naught squared u squared c squared plus m naught squared c to the 4th times 1 minus u squared over c squared, all divided by 1 minus u squared over c squared. And this first term is the momentum. So let's break this up. So I do this, break it up, and now I write m naught squared u squared c squared divided by 1 minus u squared over c squared plus one more term, which is m naught squared c to the 4th times 1 minus, and that's it. It's actually 1 minus u squared over c squared divided by 1 minus the same quantity, 1 minus u squared over c squared. So these two terms cancel. This term right here is the same thing as p squared times c squared. So I get a relationship or an equation, p squared times c squared plus m naught squared times c to the fourth is equal to the total energy squared, which is the kinetic energy plus the rest mass energy, quantity squared. And that is the last derived quantity that we need or that we have. So notice that here I can calculate, knowing either the momentum or the kinetic energy, I can calculate one or the other. So let's take the square root. So I can say, for example, that EK is equal to the square root of p squared times c squared plus m naught squared times c to the fourth minus m naught c squared. And so if I know what the momentum is, I can calculate what the kinetic energy is. Right? So I have a new relation between momentum and kinetic energy. Remember, the old relation was that the kinetic energy was equal to 1/2 p squared, or p squared over 2m, right? Right? That was the old relation for momentum and kinetic energy. This is the new relation between energy and momentum. Of course, at low velocities, when the velocity is small, then this equation has to become, we have to show that that in fact becomes the same equation. But this is the relativistic equation. So now we've got basically all the equations we need. In fact, we've got the momentum is equal to m naught c squared, I'm sorry, m naught u, m naught times u, divided by the square root of 1 minus u squared over c squared. So this is 3 equations that you have. You have an equation here for kinetic energy related to momentum. I have the relation between momentum and velocity. And those equations, or I should say this equation and this equation, are now the ones, these 2 equations replace what we had before. So this is equation 1, and this is equation 2. And these are the new equations for energy and momentum. Okay? And these 2 equations now allow us to do whatever calculations we want. So let me make one more comment before you go. Notice that all of these equations, whether we're talking classical or the new ones, have 4 parameters: mass, velocity, kinetic energy, and momentum, right? The basic truth of both of these systems, whether it's classical, is that if I know any 2 of these, I can calculate the other 2. Okay? If I know any 2 of these 4 variables, I can calculate it from these equations relativistically, or I can calculate it from these 2 equations, non-relativistic, right? If I know mass and velocity, I can calculate momentum and energy. If I know mass and kinetic energy, I can calculate velocity and get momentum, right? The same principle holds with these, except they're a little more complicated, okay? And they're a little more tricky to use. So next time we're going to have a whole hour devoted to how do you use these equations. And what it means is we have to have a new system of units. We're no longer going to be using joules, kilograms, meters. We're going to be using electron volts. We're going to have a new system of units, and we'll talk about it. But for now, you've got enough homework to just do the rest of the stuff before we, because I haven't assigned the kinematic problems yet. This is going to be homework number 3. And then we're done.